Okay, so this week we start looking at the crack tip fields when plasticity at the crack tip is large scale. So small scale yielding assumptions no longer hold and there is plasticity at the crack tip. Under these circumstances, the first theory that we are going to look at is a simplified plasticity theory called slipline field theory, which assumes a number of things that make the construction of the plastic field somewhat simpler. I'll come to that in a moment. Let us look at the assumptions first. The deformation is plane strain and u3 is equal to 0. u1, u2 are functions of x1, x2 only. So the stresses that we are interested in this case are completely the two-dimensional stresses, all that can be drawn on the plane of the slide. So sigma 1 1, sigma 2 2, sigma 1 2 are the stresses that we are going to look at. The displacements that we are going to look at are u1 and u2, and each of these things are functions of x1 and x2 only. So that is the first assumption. One follows from the other. The assumption about the stresses follows from the assumption about the displacements. So the second is it is rigidly perfectly plastic. It is characterized by its yield stress in shear. That's what we are going to characterize it by. So tau y is the yield stress in shear, which is 1 by square root of 3 of the yield stress in tension. We have seen this already. And this quantity tau y will play an important role in what we are going to do in this lecture. So the loading is of course quasi-static and temperature plays no role in this loading. So with these assumptions, we can construct what is known as a slip-line field for a problem where we have rigid perfectly plastic situation. Rigid perfectly plastic means, as we have seen before, that the elastic strains are neglected. The entire strain is plastic strain. We have large scale plasticity, remember, and it's a perfectly plastic, so there is no expansion of the yield surface. The yield stress in shear remains constant irrespective of the plastic strain, which in Ramberg-Osgood terms uh, means that the hardening exponent tends to infinity. We have seen this in the earlier slides as well. So with this, we can construct what is known as a slipline field. We are not going to look at how the slipline fields are actually constructed. Because that's not easy to do and would require a much longer set of lectures. What we are going to do is we are going to learn how to interpret the slipline fields. Okay, so we will just concentrate on the interpretation of them. So we also assume that there are no body forces, and with these assumptions we can construct what is known as a slipline field. So let me explain what these slipline fields are. The slipline fields are a set of lines called alpha lines and beta lines. So in my drawing, these are the alpha lines. These are the alpha lines. These are the alpha lines and these are the beta lines. And the entire region which is undergoing rigid perfectly plastic deformation can be covered by a net of alpha lines and beta lines, the angle between them being always equal to 90 degrees. So alpha lines and beta lines are a set of orthogonal curvilinear orthogonal curvilinear system, which covers the entire region that is undergoing rigid perfectly plastic deformation. Now, what are these alpha lines and what are these beta lines? Let us try to understand that. So to do that, you need to have these two axes. These are the global axis with coordinate with base vectors e1 and e2. And suppose you have a stress state, a two-dimensional stress state, which is characterized by these three components. Okay, so you have these three components of stress at a particular point in this entire region, that at a point in this region which is rigid perfectly plastic. Now I can use the Mohr circle. So this point represents my, let's say, my one plane, and this point represents my two plane. So I can plot sigma 1 1. This is sigma 1 2 at the point, and then I can plot sigma 2 2 and then sigma 1 2 on the other side, join these 2 points, draw this Mohr circle. And if I draw this Mohr circle, then I can identify two quantities. One is the maximum principal shear stress, which I obtain by turning the point 1, point representing plane 1, by an angle of 2 phi, which represents a physical turning of the axis by an angle phi. Remember, Mohr circle is just a way of stress transformation in two dimensions. So when I turn this by 2 phi, I actually turn the physical axis by phi, and I reach this point where I have a state of stress which is characterized by the maximum shear stress, and the mean stress body. So the two variables characterizing this point are the maximum shear stress and the mean stress, and the maximum shear stress in this case has to be equal to tau y. The maximum shear stress has to be equal to tau y, and because it is rigid perfectly plastic, so the shear stress, maximum shear stress, is known to be tau y, and then this mean stress is an unknown. It's a variable in the problem. So there are two variables that characterize this stress state. One is, of course, the mean stress, and the other is this angle phi by which I have to rotate. The one plane in order to get to the maximum shear stress plane. So if I draw it here, when I rotate this by phi, I get to this coordinate system E alpha, E beta. So this is my alpha point, and 90 degree apart is my beta plane. So when I turn it by alpha, remember is the angle between one and the alpha plane, one plane and the alpha plane. So when I turn it by just alpha, then I reach this E alpha, E beta coordinate system, in which the if I draw a pillbox here, this pillbox is under a pure shear state with a superimposed hydrostatic stress. So the hydrostatic stress is this, and the pure shear, since it is rigid perfectly plastic, has to be equal to tau y. So the pure shear stress is tau y, and then there is a superimposed unknown hydrostatic stress. So if I do this at every point turns by a different angle alpha. So I will be able to trace out these black curves, which are the alpha lines, and then perpendicular to the black curves, I can trace out the beta lines in such a way that at any point, if I orient my pillbox around the E alpha, E beta direction, which is tangent to the curves, tangent to the alpha and beta curves, I will reach a state of stress which has tau y as the shear stress and a superimposed hydrostatic stress sigma bar. So this is the significance of the alpha and beta lines. Along the alpha and beta lines, you have a purely shear state of stress with a superimposed hydrostatic stress. Now, if you know sigma bar, if I have a way of knowing sigma bar, and if I know this alpha, then I can use simple geometry. Say I know this alpha, I know this sigma bar, then I can get back what is the sigma 1 1 and sigma 2 2 and sigma 1 2 from these simple geometric formulas, which are also, you can get it from two-dimensional stress transformation. So these are these are easily obtained. So if this angle is 2 phi, this angle is 90 degree minus 2 phi. So you get sigma 1 1 as sigma bar minus tau y sine 2 phi. Sigma 2 2 is, this is also 90 degree minus 2 phi. So sigma 2 2 is sigma bar plus tau y sine 2 phi. Sigma 1 2 is tau y cos 2 phi. It's because this is your sigma y. So now we have two variables, sigma bar and phi, replacing the three stress components. And what we are going to show is along the slip lines, these two quantities have a special relationship which can allow us, if we know the slip line net, it allows us to find these two quantities. And then once we know these quantities, these expressions help us back out the stress components at any point. So this special relationship between these two quantities along alpha lines, let us find that. So what we are going to do is we are going to write the equilibrium equations which have to be satisfied at each and every point, and then take these stress components and plug them into the equilibrium equations. In two dimensions, these are the equilibrium equations. These are the equilibrium equations. And then I have taken these expressions, these three expressions for the three stress components, and have plugged them into the equilibrium equations. The equilibrium equations are now in terms of sigma bar and phi. There are derivatives of phi and derivatives of sigma 1. Now along an alpha curve, if you move along an alpha curve, d sigma, the variation in d sigma bar will be d del sigma bar del x1 dx1 plus del sigma bar del x2 dx2. This would be the variation according to chain rule along an alpha curve, which is the black curve here. Now this dx1 and this dx2 can be written as cos phi d alpha and sin phi d alpha. That's easy to see because this angle is alpha, this angle is alpha, this is your d alpha, this is dx1, this is dx2 when you move a small distance along this. So this angle is phi. So dx1 is d alpha cos phi, dx2 is d alpha sin phi. So that's what I have plugged. So yeah, d alpha cos phi and d alpha sin phi, and that's what I have plugged in here. And now you can substitute the expressions for sigma bar 1 and sigma bar 2 from these two expressions, and then you get d sigma bar along an alpha line to be equal to 2 times tau y d phi. So if you move along an alpha line, the change in the mean stress is equal to 2 tau y times the change in the angle. So if you measure the change in the angle along an alpha line, if you measure the change in the angle along an alpha line, and from that you can use this expression to get the change in the mean stress. And once you know the change in the mean stress, you can use these transformation relations in order to find the stresses at the point. So this is something that you need to remember, that along alpha lines d sigma bar is equal to 2 tau y d phi. You can do a similar exercise like this along the beta lines, and we get what are known as the Henke equations for the slip line field. So sigma bar minus 2 tau y phi is constant along alpha slip lines, and sigma bar plus tau y phi is constant along the beta slip lines. So these two are going to be our guiding equations for interpreting the slip line field. We are not going to learn how to draw slip line fields because that's going to be involved, and that's not easy to do, and that's not possible within the time we have in this course. But we are going to learn how to interpret them. So in order to facilitate the interpretation, the Henke equations are going to come in very, very handy. We have another set of slip line equations which are called Gehringer equations. Uh, so these Gehringer equations connect the velocities or change in displacement along the slip line fields with each other. So along the alpha slip line fields, uh, you have you have this as the connection between phi and the velocity. So if you know the change in phi along the alpha slip lines, you can get the change in velocities. Similarly, along beta slip lines, if you know the change in phi, you get the velocities as well. But these Gehringer equations, we are not going to use. I am just mentioning them for the sake of clarity, for the sake of completeness. Uh, but we are not going to use them in this in interpreting slip line fields. It's just for your information. So how do we use the Henke equations? How do we use the Henke equations? And there are a couple of things that you need to that are easy to find out from the Henke equations. So let's take this small example of a rigid punch. So this is my rigid punch subjected to a load P. And in this case, we assume that this entire region under the punch is perfectly plastic, is rigid, perfectly plastic. So we are going to draw the slip line net uh, representing this problem. So to draw the slip line net, we have to we have some simple deductions from these transformation equations that we have seen. Remember, through the slip line fields, we are planning to find sigma bar and phi using the Henke equations, which says that along alpha slip line, uh, sigma bar minus 2 tau y phi is constant, and along a beta slip line, sigma bar plus 2 tau y phi is constant. So we know these things. You're going to use this to find phi and sigma bar. So now, let us look at a free surface. There are no body forces. We have already discounted body forces in this problem. So in this, the normal is in the 2 direction. Therefore, this is a free surface. Sigma 1, 2 and sigma 2, 2 will be equal to 0. If sigma 1, 2 is equal to 0, that means this is equal to 0. Then cos 2 phi is cos 2 phi is 0, and therefore phi is plus minus pi by 4, is plus minus pi by 4. And therefore if you have a free boundary, phi, remember, is the angle between the alpha slip lines and the free surface. So the alpha slip lines will make an angle with a free surface. So this is your x1, this is your x2. So this angle will be plus minus pi by 4. So the alpha slip lines at a free surface can either be like this, which makes an angle of plus 45 degree, or be like this, which makes an angle minus 45 degree. So when the alpha slip lines and beta slip lines are mutually perpendicular, so when the alpha slip lines make an angle of plus 45 degree, beta slip lines will make an angle of minus 45 degree, and vice versa. So the alpha slip lines will meet the free boundary at an angle of plus minus pi by 4. Now, here in this case, if this is equal to pi by 4, if phi is equal to pi by 4 close to the free surface, then this is sine 2 phi is sine pi by 2, which is 1. So sigma 2 2 will be sigma bar plus tau y when phi is plus 45 degree, and minus tau y when it is minus 45 degree. Okay. Similarly, sigma 1 1 will be either sigma 1 1 will be either sigma bar minus tau y in case phi is plus 45, and will be equal to sigma bar plus tau y in case it is minus 45. So sigma 1 1 will be sigma bar minus plus tau y, and sigma 2 2 will be sigma bar plus minus tau y. The plus and minus is determined by the angle that phi makes with the free surface. So sigma 2 2 is equal to 0. Sigma 2 2 is equal to 0 at the free surface. Therefore, sigma bar at near the free surface will be equal to minus plus tau y. Sigma bar will be equal to minus plus tau y, and therefore sigma bar is minus plus tau y, means that sigma 1 1 will be equal to minus plus 2 tau y. Now, how do I determine the correct sign? To do that, I have to be able to guess what is sigma bar going to be, whether it's going to be compressive or tensile. So if it's going to be compressive, then I know that sigma bar is minus tau y. Sigma bar is minus tau y, which means that I'm taking the minus sign. Therefore, I'm taking the upper sign, so that is minus, and that corresponds to theta equal to pi by 4. Okay, and then sigma 1 1 in that case will be equal to minus 2 tau y, because I have taken sigma bar. I have been able to deduce that sigma bar is equal to minus tau y. So I have to look at whether it is compressive or tensile, whether the mean stress is compressive or tensile, and based on that we will be able to determine the sign of theta, or in this case phi, I should write sign of phi that we need to choose. Okay, so in our case we have a punch which is pressing down on this rigid surface, or on this perfectly plastic surface, rigid perfectly plastic surface, and therefore the angle phi, we expect sigma bar to be compressive somewhere here, and therefore this angle phi will be plus 45 degree. So it will not be minus, it will be plus 45 degree, and so these are my alpha lines, and therefore the beta lines would be these. Okay, so that is at the free surface. What about somewhere here? Somewhere here, sigma 2 2 is equal to sigma applied, where sigma applied, let's assume that this is a perfectly lubricated punch. So at this point, the normal is still in the two directions. So sigma 2 2 is something like punch force by punch area. Sigma 2 2 is this, and sigma 1 2 is equal to 0. If it's a well lubricated punch, there is no force in the x direction, so sigma 1 2 may be taken as equal to 0. So sigma 2 2 is something. Sigma 2 2, let's say it's equal to sigma applied, where sigma applied is equal to p by a. So sigma 2 2 is equal to sigma applied. Sigma 1 2 is equal to 0. So if you put sigma 1 2 equal to 0 here, you still get that phi is equal to plus minus 45 degree. And then sigma 2 2 is sigma a, which is equal to sigma bar plus minus tau y, because sine 2 phi is either is plus 1 when phi is plus pi by 4, and minus 1 when it's minus pi by 4. So it will be plus minus tau y. So now you have to guess whether this is going to be less compressive than this. So here, if we expect that this will be more than this, both will be compressive, but this will be more than this, then this is how your Morse circle will look like, and you can then easily guess that the alpha lines will make angle equal to minus pi by 4 with the x1 axis. Okay, so how do I do that? I assume that sigma bar, so let me go back to the equation that I wrote. So sigma bar is equal to sigma A minus plus tau y. So I have already assumed that both this and this are compressive, but this is less compressive than this. Therefore, tau y I have to take the positive sign of tau y in order to make this as more compressive than this. If I take the positive sign of tau y, then I have that corresponds to the negative sign of theta and negative sign of phi, and that's why I have to take phi equal to, in writing theta everywhere I've changed that, phi equal to minus pi by 4 the punch. So here the alpha angles will make an angle of minus pi by 4 with, so this is actually minus pi by 4, minus pi by 4 with the x1 axis. So in regions where we have either stress-free condition or we have sigma 2 known, as is the case here, we can locally find the directions of the alpha and beta lines. We will not go beyond that in constructing the slip line field, and I'll directly give you the slip line field for this problem, which others have drawn. This slip line field. So this is called a rigid region where the slip lines are straight. Slip lines are straight lines. So you can show that in this region where the slip lines have to be at an angle of 45 degree, they cannot change direction, because if they change direction, under in a region where they have to be strictly 45 degree, if they have to change direction, phi will change, and if phi changes, sigma bar will change. So since that cannot happen, we come to the conclusion that there would be regions under the punch where the slip line fields have to be, so regions under the punch and under the free surfaces where the slip line fields have to be straight and at plus minus 45 degrees to the x1 x1 x2 equal to 0 plane. So these are called rigid regions. These are called rigid regions because the slip lines are straight here, and therefore sigma bars are constant here. But these regions have to be connected by these fans, and these fans are where the slip lines are curved. At least one of the slip lines, at least either the alpha or the beta slip line, is curved, and therefore phi varies in this region, sigma bar varies in this region. So these regions have constant sigma bar. They're connected by these regions where sigma bar is varying. So these are like intervening regions which are going to connect the rigid regions. So so far we need to see only rigid regions and the fan regions. And how do we interpret the slip line field that we have seen? So to interpret the slip line field, we start with the equation, the Henke equation, along, let's say, an alpha slip line. So these are the alpha slip lines. So this is the alpha slip line. We know along the alpha slip line, phi doesn't change along this part, so sigma bar doesn't change either. So up to this, sigma bar is unchanging, and then it changes through this part, and then again it's unchanging here. Going from here to here, here to here, you see a turn of pi by 2. So the alpha slip lines turn by pi by 2, which means this angle phi turns by pi by 2. And then we can use the Henke equation, which says that sigma bar at in the part DEH, in the rigid part DEH, so that this part, connecting the sigma bar to this part, EFI, and then 2 tau y phi, which is pi by 2 in this case, change in phi, which is pi by 2. So this is tau y pi, and the difference in the mean stress here and here should be equal to tau y pi. So this is the difference. Now in this region we actually know sigma bar. We actually know sigma bar, and it is equal to minus tau y. It is equal to minus tau y. So I can use, I have already found that. I have already found that sigma bar equal to tau y plus tau y in EFI. So I immediately, using this equation, I get that in this region, that is under the punch, sigma mean has to be equal to minus 1 plus pi tau y. So if I know sigma bar, I can immediately find sigma 2 in this rigid region where phi is equal to pi by 2, and I find sigma 2 is equal to this. This is the sigma 2 under the punch, which means that the total load that you have to apply in order to cause plastic deformation, rigid plastic deformation in this region, is the width of the punch times this force, and you have to apply it, of course, in the compressive direction. You have to apply a force in the downward direction, and this force will cause a rigid plastic deformation of this sort in the punch. So directly you get the punch load that is needed in order to plastically deform the substrate. So this is a quick estimate of the punch load that you can get from the slip line field theory. So now this punch problem is actually very similar to a mode 1 crack problem, which we will see in the next lecture. So let us try to interpret the slip line field in front of a mode 1 crack. Now remember, we are characterizing the material around the crack tip as rigid, perfectly plastic, and we are also assuming that large scale plastic yielding is occurring at the tip of the crack, near the tip of the crack. The crack faces are traction free, so these are traction free surfaces. So phi at these surfaces has to be plus minus pi by 4. That means the alpha lines have to make plus minus pi by 4 angle with the x1 direction, with the x1 direction. So whether it is plus or minus will depend on the sign of the hydrostatic stress. So hydrostatic stress we assume is positive here, positive here. Therefore, the alpha lines have to make an angle. Remember, hydrostatic stress sigma bar is minus plus tau y. So it has to be plus tau y in our case, so that phi has to be minus pi by 4. So these are the alpha lines that are making minus pi by 4 with the crack face in this region, which is going to be a rigid region. This region is the rigid region where the hydrostatic stresses are constant, and because it's a mode 1 problem, it's symmetric, so we'll have a rigid region here as well. Okay, now in so in front of the crack tip, in the region let's say FEG, so this region, you have another rigid region where the stresses are, hydrostatic stresses are constant, and these two rigid regions are connected by a fan where the stresses are varying along the beta direction. So these are the beta lines, so stresses are varying in the beta direction. Now I know the hydrostatic stress here, and I know that it is equal to plus tau y. Sigma bar is equal to plus tau y here, and then as you go from FD to FG, you have a phi change in phi of 90 degrees, which means that you have 2 phi is equal to pi. So and you are traveling along a beta line. This is a beta line. Therefore you have sigma bar plus 2 tau y phi is constant, which means that the sigma bar here and the sigma bar in this region will be related by tau y plus pi, plus, because you're going around along a beta line, plus pi times tau y. So it will be equal to 1 plus pi tau y. So here in this region, the sigma bar is 1 plus pi tau y. And once you know sigma bar, uh, you can find out sigma 22 and sigma 11. So sigma 22 and sigma 11 are also constant in this region, and these are the values of sigma 22 and sigma 11. What you will see is that this is exactly similar to the punch problem, except that the signs are all reversed. Now, uh, so what are the stress fields in front of a plastic crack where the material is assumed to be rigid, perfectly plastic? It's shown here. There are three regions in front of the crack tip. In this region, this is the rigid region, sigma 11 is 2 tau y, sigma 22 and sigma 12 are 0 in this region, just behind the crack tip. In this region, this is another rigid region. Sigma 11 as we have found, sigma 22 as we have found is this, sigma 11 is this, and sigma 12 is equal to 0. That's the rigid region. In between, you have this fan region where the stresses are varying in the beta directions, and they're varying in this manner. You can easily figure that out from the solutions. So they are varying in this manner. Uh, since this is a mode 1 problem, uh, you have exactly the same stress fields below and above the crack tip. Now let us look at a mode 2 case. Now let us try to interpret it for the mode 2 crack. So for the mode 2 crack, there are significant differences. First of all, this is an antisymmetric case. So since it is an antisymmetric case, the mean stress above and below have to be of different signs. Let us assume above it is equal to minus tau y, and below it is plus tau y. This surface is attraction free, therefore sigma 22 and sigma 11 are equal to 0 on this face as well as on the lower face. So sigma bar is minus plus tau y as we have found out. So let us say it's minus tau y above and plus tau y. So phi will be equal to 45 degrees, plus 45 degrees on the in this rigid region. Now also on this line, that is on the theta equal to 0 line, you must have sigma 11 and sigma 22 equal to 0, because this is a antisymmetric problem, and sigma 12 will not be equal to 0. Now, this is a trial slip line net that we have generated, and this is actually not going to work. That's what I want to show. So in here it is the stress is minus tau y. The mean stress is minus tau y. This is a rigid region. This is also a rigid region. So here also it should be equal to minus tau y. So on this line it is minus tau y. On this line, so in between these two, there's an angle of pi by 4. So when you go from here to here, you turn by pi by 4. So 2 tau y pi by 4 is what you add to the stress on this line, which is equal to the mean stress on this line, which is equal to minus tau y, and you get pi by 2 minus 1 into tau y as the mean stress here. Mean stress here, which is not obviously equal to 0. This is not equal to 0. The mean stress has to be 0 because sigma 11 and sigma 22 has to be 0 for this antisymmetric problem. So this trial net is not going to work. What you have to do to make it work is you have to add small sector in between, so that the change in the change in this sector, so you have to add a fan in between the two rigid regions, so that the change here and the change here together make the stresses equal to zero, the mean stress equal to zero on this line. So as I said, the alpha lines make an angle of plus 45 degree here. So these are the alpha lines. Then these alpha lines continue in the second sector. Okay, but the angle between the alpha lines have changed now, because they are no longer 45 degrees, because you have added this sector in between. So you have to uh, earlier in this net, this angle was pi by 4. Now I have added a smaller sector here. So and here what changes are, so these are the alpha lines are changing direction. So the change in phi is due to alpha, so I call it delta phi alpha. Here, these are the beta lines. These are the beta lines that are changing direction. So there is a change in the phi due to beta, and I call that delta phi beta. And these two together has to be equal to pi by 4, because the original angle was pi by 4 to start with. So this is the first expression that I have, pi by 4. And then on coming from here to here, I must reach zero mean stress. So to do that, I calculate the sigma y. So first I start with minus tau y. So minus tau y is here. Then the angle changes along a alpha line by delta phi alpha. So that will lead to a minus. So minus, it's along alpha line, minus 2 delta phi alpha tau y. And then again here it will change by an angle delta phi beta, because this angle is delta phi beta, but this change is along a beta line, so it will come with a plus. So it comes with a plus. So this thing has to give you equal to 0. This thing has to give you equal to 0, and you can solve these two equations. So this equation and this equation together, if you solve, you get theta 1 equal to 36.82 degrees, and the other one, pi by 4 minus theta 1, as 8.18 degrees. So this is your 8.18 degrees, and this is the rest of the 45. So for uh, the mode 2 case, this is the slip line field that you have. So you have this rigid region here, where sigma 1, sigma 2 2 and sigma 1 2 are equal to 0, and sigma 1 1 is equal to tau y. This is another rigid region where these are the stresses. These stresses, in order to find these stresses, I have used this 8.18 degrees, which is the angle that this small region makes, small fan makes, with regions 1 and 3. And then on this line, sigma 1 1 and sigma 2 2 are equal to 0, and sigma 1 2 is equal to tau y. So this is the slip line field for the mode 2 case, and this is the slip line field for the mode 1 case. So this is assuming that you have rigid perfect plasticity, and these are the fields that you would get if large scale yielding was occurring in your material. Okay, so we stop here with the slip line fields. Now we will look at a material that is not linearly, not perfectly plastic. We'll look at a material that is not perfectly plastic and try to see what the plastic fields would look like in case of large scale yielding.